Tucson Spring Technical Workshop. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks. As you know, we had to cancel the physical meeting due to the coronavirus situation, and after consultation with our session chairs, we decided to proceed with a shortened online version. So we're holding webinars for the 2 plenary and the 10 technical sessions. We began in mid-March, just a week or so ago, and we're running through early May, approximately twice a week. You can find the full schedule at www.esig.energy under the Events tab. Recognizing the limitations of a webinar with typically more than 100 people on the line, we'll have individual presentations of 10 minutes or so, followed by 5 minutes of discussion, moderated by the session chair. The lines will be muted, so we ask you to use the question box in the lower right-hand corner of your screen and not the chat box. I repeat, not the chat box. Today, we'll be hosting Session 2, Synchronous Condenser and Control System Considerations for Weak Grid Applications, chaired by Bob Zabadil of Enernex, a Chazy company. Bob is the Chief Operating Officer and co-founder of Enernex. He's been involved with the modeling, analysis, and simulation of power systems for most of his career, which spans over 40 years in the industry. Bob's the previous chair of our Reliability Working Group and a good friend. Bob, I'm going to turn it over to you now.
All right. Thank you very much, Charlie. I want to get on to the presentations, but first, just a few remarks. I want to commend Charlie and the ESIG board for the decision to soldier on in these trying times. I remember seeing the draft program as it came out early in the year for the Tucson workshop, and how outstanding it was. I was really looking forward to the Tucson workshop. Oops, excuse me, dropped the headset. So in spite of the circumstances, I think this is the best way for us all to proceed. Our topic for today is really synchronous condensers, and one could ask, is what's old new again? Because synchronous condensers have been around, have been used for quite a while over the last century. Less recently, but today we'll hear about some of the attributes that are bringing them back to the forefront in light of increasing penetration of inverter-based resources and renewables. So some of this will be kind of a review of an undergraduate course in electrical machines, but we will hear a lot more about the specific benefits, cost, performance, and potentially pitfalls of synchronous condensers. So moving on, I'd like to introduce our first speaker. Many of you, I'm sure, know him, Nick Miller, who recently retired from GE after 3/8 of a century of work on bulk power systems, a lot of that associated with wind and other renewable integration over the last 20 years. We're going to try to move along and keep the presentations flowing to allow for some questions to be answered after each presentation, and then hopefully have a little bank of time at the end to loop back and pick up some other questions. So with that, I'll turn it over to Nick and remind him that in light of his 3/8 of a century of service, that he has 1/96th of a day for his presentation. So Nick.
All right. 196 and counting. Thanks, Bob. Hi, everybody. It's great to be back on. And thanks for scheduling me first on this. This is a brand new deck for everybody, so we'll see how it plays. I've been chewing on this question of stability, weak grids, condensers for a bit, and I have some pretty basic tutorial material that most of the people on the call will recognize, but maybe we'll get the blood circulating relative to the challenges at hand a little differently. So bear with me if you feel like I'm giving you a freshman lecture, but hopefully this will be useful. Oops, the wrong button. Oh no. There we go. Okay, so this is a pretty simple narrative, most of which you know. I'm going to talk about the problem of getting power out from relatively remote generation sites. That is an issue common to a lot of the stability questions that we're faced with and that are driving the desire for synchronous condensers. And I start here with some real basics that basically the idea that and the reality that getting lots of power out of the remote generation has always been a stability problem. And we are still faced with that, but the stability problem is a little different. And the question here is the use of condensers to help us bridge or prepare for new future really the right thing? So with that, let's go on. So in true to form, I've reduced everything to a really simple cartoon, and we're going to use three very familiar stability tools to talk about this problem. So my export problem, and you know, those of you that listen to my grid forming lecture a few weeks ago will recognize some of these drawings, but I've repurposed them for this issue. So we've got an exporting system that's trying to push power through impedance to a system. And we have a choice between synchronous generation as the old world and inverter-based resources, new world. And we're going to use three tools that have been in widespread use, but rarely are shown at the same time. And I think that's an important piece for this discussion. So we go forward. Those of you who've been listening to me lecture for seemingly a really long time will recognize this slide, which I've been using since 2005, my GE days. And this is a radial system of almost exactly the topology of my cartoon. It happens to be a simulation of the Colorado Green wind farm, but you don't really care. It's 160 megawatts. And this is all things being equal, a wind plant versus a synchronous machine of the same loading and rating. And again, you'll recognize all of this stuff. On the left is a primary cleared fault, and the synchronous machine in red swings and stresses the stability of that system. The black curve is the wind plant, which behaves radically different. So what I want to do here is dive into the basics of that behavior and where we're coming from and why it looks different with synchronous, without synchronous machines. So in each one of these, the following sequence of 6 or so slides, I'm using the same figure on the left and the red dot. So I love doing things color coordinated, and then every once in a while I get abused because people are colorblind. So this slide is all red and green, so sorry for all you colorblind folks out there, but we're looking at the red dot, and across the bottom are these three tools that we are accustomed to using. The equal area criteria tool, which is classic transient stability tool. The center one is a PV curve, which is the classic tool for evaluating voltage stability. And then on the far right is the power transfer phasor diagram, where the angular separation of the sending end voltage and the receiving end voltage and the midpoint voltage look very familiar, with driving home the emphasis that that midpoint voltage is on a straight line, not on the arc, the constant voltage arc of the drawing. So everybody knows this stuff. So let's look at what happens when we put a fault on. So this 1000 or 100.2 slide is the instant that the fault is applied. There's been no acceleration of the inertia of the synchronous machine. The voltage is collapsed. It goes down to some point related to the apparent impedance and the fault current delivery of the synchronous machine. The voltage, the PV curve is collapsed. And in general, during the fault, we are on the underside, the unstable locus of the multi-root equation of the voltage stability. So the red arrow shows where the red dot has migrated to. Sending end voltage has collapsed but hasn't moved yet. So we all recognize that. The next slide here is at the end of that disturbance. And again, all familiar to you, right? The voltage has further sagged as we suck some of the flux out of the machine. The system now has pulled apart. The sending end voltage phasor is moved out, but it's still deeply depressed. And the orange hashed in space is the energy that inertia, which in this case is not really our friend, has accumulated in the course of the fault and needs to dissipate. So we all know that. And let's clear the fault. And at this point now, the voltage can come back up. It doesn't come all the way back up because the flux has been collapsed out of the machine to some extent. But the angle doesn't move more than that, right? No time has elapsed, so the state variable of the angle hasn't moved yet. We start to export power. We've moved way out on the voltage on the nose curve, and the power is substantively higher than it was pre-disturbance. If it isn't substantively higher, the game is over because we need to dissipate the energy that the synchronous machine has accumulated during the fault before it rips off the grid. So we go on to this, and this is now at the peak of the power swing. All right, so the angle has moved further out. We're up that sine wave, right, that half a sine wave. And at the point where the excess energy dissipated by having that angle be greater than, and the power be greater than that being pushed into the drivetrain by the turbine, the machine stops accelerating and decelerates and proceeds to bounce around, hopefully in a damped fashion. So everybody should recognize this. You may not have been used to seeing the PV curve with the equal area curve and the phasor diagram all at once. But otherwise, this is stability 101. And just to remind you, again, this is, I've been using this slide for this figure for 15 years. If the fault is too long, then the energy accumulated by the machine during that point when it can't get the power out, but the power is still coming into the drivetrain, is such that it can't be dissipated. So the orange rectangle-y thing is bigger than the orange triangle thing. We slide over the top of the PV curve, the phasor angle pulls apart, the midpoint voltage collapses, and you are toast. On the other hand, now, let's look at what happens with an inverter-based resource. This could be solar or wind. Right? This is now back at the time of the fault inception. The pre-disturbance condition is the same. The voltage collapses during the fault. The voltage collapses further because the inverter-based resource doesn't deliver as much fault current. So the during fault equal area curve is lower as the black dots show. You're farther down the collapsed PV curve, and the situation is not good. But because it's inverter-based, we do not need to worry about the power. What happens to the energy during the fault? The energy during the fault in the PV curve, in the case of photovoltaics, just goes away. In the case of wind turbine, it goes into accelerating the wind turbine. The wind turbine speeds up, but that doesn't mean that it's angle pulled, the synchronous machine. So when we clear in this figure, we are now not particularly farther out on the PV curve. And if the phase lock loop has not gotten confused about where it is, the angle hasn't changed substantively and the power is very similar. So we're at a really radically different place that's quite a bit friendlier at the end of the fault. So that's good news, but typically we see in studies and other kinds of things, because the system can handle more power, we go ahead and use it up. So we're going to go past the stability limit of the synchronous machine and put some more power in. That's what's conveyed in this figure. But in practice, that infinite world isn't there, and there's a lot more complexity to my little cartoon. So one of the things that becomes rather important here is that the rest of the system actually does move around, and there's no such thing as that infinite sending end, and the system is more complicated. happens is that everything moves. And the phase lock loop, the control of the inverter-based resource, tries to keep up and tries to keep P, the black arrow, more or less fixed, unless it's got some other instructions. So the sending end phaser will chase the receiving end phaser in a fashion that keeps the behavior that you saw in the previous slides more or less the same. It's not like it's truly just sitting there. That doesn't happen. That becomes important now when we go to worrying about weak grid. So we go to weak grid, and I used this slide a few weeks ago, and you'll recognize it. It's got quite a bit of information on it. But basically, the idea is that the inverters at that sending end need a minimum short circuit strength to behave themselves and to not get confused. There's lots of aspects about confusion, but one of the two primary applications of synchronous condenser is to stiffen that bus so that the inverter behaves itself. But now I've introduced something that kind of looks like the synchronous machine. So now I've continued with my color coding. My infinite world is no longer infinite, that's red, but I've got a synchronous condenser which is done in purple here. I want to distinguish the two things. So now the phase lock loop tries to maintain the power export by chasing the sending and the receiving end voltage, but the angle of the synchronous condenser can't move instantly. It's a state variable and it has inertia associated with it. So the synchronous condenser supports the bus. That's good. It delivers current to keep the voltage healthy. It delivers system strength to help keep the inverter stable, but it gets left behind. And it then, because it's relatively low inertia constant typically of 1 or so, it will get dragged because it has no prime mover and try to realign itself with the sending end DS of the inverter, and it bounces around. And if you don't get it right, that bouncing is unstable and the synchronous condenser rips off and you have a stability problem. So we've gone possibly from out of the frying pan into the fire by the addition of the condenser. Not necessarily. It's a concern. It's not fatal. So now let's ask the question, what might happen with as we move on from fixing the problem with synchronous condenser to fixing it with grid forming. By having a grid forming inverter, I ought to be able to not have to support that sending end voltage to keep the control stable. That was the whole point of that. So if I don't have to do that, then I don't need the condenser, but I need to tell the grid forming inverter to chase the receiving end system. Otherwise, I end up back with the same problem I had with the synchronous machine, which was that it was unstable. So the grid forming inverter does not want to look like a synchronous machine. Otherwise, I have to back the power transfer. But it wants to maintain voltage and it wants to chase. So somewhere it needs to be better than the grid following inverter and better than the synchronous machine. And we've got a little work to do with that. So then the next problem here is that these systems are actually long and stringy, and we got to support the voltage in the middle. All right? So now I'm going to concentrate on the orange middle here. So I've got some compensation. And remember, if you look at the phasor diagram on the right, if I support the voltage in the middle, then that tent pole is bigger. It's no longer in the straight line between VR and VS. The nose curve gets better in orange. The power transfer curve gets better in orange, and everything is improved by the presence of some compensation in the middle of the line. But as I push the system out, it gets progressively more brittle. And on this slide, you see the variations in the different kinds of supports. So synchronous condensers don't have hard limits. They are slower, but they don't have hard limits on their current delivery. So they tend not to bang into limits, as this drawing suggests, between shunt banks, SVC, and StatComs, all of which have hard limits. So condenser is going to be, in some regards, a better mannered compensation than the other ones. And it also contributes short circuit strength to make the inverters back upstream behave better. But it's not as close, so it doesn't do as much good. So when these systems bang hard into limits during swings, things like SVCs and StatComs run into limits. So this simulation I dug up from 20 years ago, I did in the days before I was worrying much about wind turbines, and you can see that the SVC and the StatComs, when they bang hard into limits, can be problematic. So there's a real rating problem. You got to figure out exactly what you want it to do. Okay, so let's get to a summation here of what we might be trading off in the condenser and the SVC world. On the left side is plus and minus with the condensers. So the condensers help the short circuit problem. They don't, they actually raise the natural frequency, which is better for the control of the inverters. They don't have hard limits, and they add inertia, which can be a good thing. On the other hand, they're slower. They have more physical time constants to deal with, and they have inertia. So depending on the problem you're dealing with, the inertia can be good or bad, and you have more constraints on the knobs. Whereas the SVCs on the other side and StatComs are very agile and very fast, but they don't contribute any short circuit. So in summary, we've got two classes of stability problems that are related but not identical. One is keeping the sending end stiff enough by adding condensers, and the other is to keep the soft middle supported enough to manage export. Those are not the same problem, although they're related. The first problem, the end, should be less necessary with grid forming resources. The problem in the middle will look a little different with grid forming resources, and you may not have as much benefit of condensers as condensers. So we have a duality here that hasn't quite gotten into our consciousness about which direction grid forming inverters are in general going to somewhat reduce the benefits of condensers, but that doesn't mean that they aren't good. And figuring out the best mix is something that we haven't done as an industry. So I'm done. A couple seconds over, but not too bad. Hey, Bob?
Yes. I'm sorry, did somebody ask me a question? Okay, well, we'll move on. Thanks, Nick. There's a question that was submitted talking about a comparison between StatCom and synchronous condenser, all things being equal, but I think we'll save that one to the end because I believe that the upcoming presentations will help shed a little more light on that, or at least get some data out so that we can come up with a sort of consensus answer. So our next speaker is Dennis Woodford from Electronics. Dennis comes to us originally from down under a fair amount of time ago, and has put his stamp on North America in his work on HVDC projects. While he was at Manitoba Hydro, he started the development of PSCAD. So we're talking to the father of one of the programs that's one of the tools that's getting increasingly mentioned with regard to these challenging problems related to IBR and renewables and that sort of thing. And after he left Manitoba Hydro, he helped found Electronics Corporation with Garth Irwin. So with that, I'll turn it over to you, Dennis.
Okay, thanks, Bob, and good day to you all, and we hope you all are staying well. And just as I mentioned from what Nick said, where I live in Winnipeg, we have how much is it now? It's 5,700 megawatts of IBRs coming in. If you take Nick's little diagram on 3 bipole DCs, and we have 13 synchronous condensers, like Nick had in his little diagram, with a total of 3,000 megabars of MVAR. So we are now infinite bus bar is down AC transmission lines towards Minneapolis. Sort of. So Nick, you did right on what we got doing here. So let's carry on now and get started. Do you have a problem on the grid? Silver bullet, this is sync condenser, right? But as we go forward, there is another side to sync condensers. I remember talking to the engineer in charge of maintaining some of the sync condensers up here. He said they take a lot of care, particularly with the H2 cooling, hydrogen cooling. And so they can interact with variable generation voltage control, and they where do you locate them? In our case, it was pretty simple. We put them right where all the IBRs came in, the inverter-based resources. So I'm going to talk a bit about the modeling part, which is part of what I was required to do. And this is a synchronous condenser model that we're familiar with. It's automatically translated into electromagnetic transients from our transient stability program, using a program we developed called DTRAN. And it sets from the power flow the initial conditions for this device, this model. And so modeling of large renewable-based systems, and this is what tends to be happening today. I'll talk about EMT-PSCAD large grids, translated from power flow, transient stability, and now PSCAD can be added to PSSE, which we've been working with, and now PSLF, but it's not yet released commercially. We have been working with GE on that. And detailed models of everything we can think of contained in a substitution library in PSCAD. You run a new case, it takes out the one that was numbered in transient stability program.
Dennis, this is Charlie here. Can I interrupt you for just a moment?
Yeah.
There's a lot of modulation on your voice, on the volume, like it's coming in and fading out and coming in and fading out. I don't know if you're on a headset or not, but
I'm on a headset. I'm trying to yell into it, but is it still that way? So tell me if it is, and I'll take. If I take it up. Okay, if I take it off, is that any better?
I can't tell you.
Anyway, let me just see what I can do here.
This is better, Dennis. This is better now.
It's better now?
Yeah, it's better now.
Okay, I took the headset off. So anyway, we model detailed models of just about everything in the EMT program. And what's happening is a trend towards large grids where more EMT is coming in. The time has arrived where renewable-based resources with an increasing number of inverters. If you do everything, all your planning in transient stability-based studies, you're starting to run a risk of results not being aligned with the actual performance when it comes online. And electromagnetic transients models are now essential as they have the capability of dealing with harmonic negative sequence effects. In addition, suppliers of inverter-based facilities, wind, solar, batteries, FACTS, the whole lot, and synchronous machines provide their EMT models with the exact code of their controls and protections and exciters of the machines. So you can anticipate adverse interactions before they are brought into service. And that is proven to be an essential product of many situations. And then we have to get, because of electromagnetic transients, you're going to use a lot of computer. And so parallel processing becomes the way to do that. And there's many cores as you've got available, whether on the same computer or on a bunch of computers. You can load in as many parallel parts of your system as you possibly can, which we can do with our eTrend Plus, the PSCAD. And each for example, if you've got a wind turbine coming in that's got sensitive controls in it, the supplier provided you, you don't want, he doesn't want or she doesn't want the program to be known what's inside it. So you'll send it to us black boxed based on a non-disclosure agreement, and that's put it on its own core. And that helps solve the confidentiality matters. But the simulations are accurately initialized from a power flow solution, the standard power flow solution, which is great help. And just to give you an idea of what this might consider the left, where you have everything modeled on a single CPU, your transient stability system, and you've got 3 electromagnetic transient systems. That all runs on one CPU, and it takes a long time. But by parallelizing it, you can speed up tremendously your solution, particularly when one manufacturer might supply their wind turbine with a 1 microsecond time step for their controls, but the network, the grid, can run on say 50 microseconds. The transient stability grid could run on 4 to 10 milliseconds. So that can all be done with a parallel system, which is what we do. Now, I'll give you as an example. This is South Australia. They have put in 3 synchronous condensers at a place called Davenport, Robertson, and near Adelaide, which is the capital city of the state. And they provide a central network location to provide inertia as the wind penetration rises. I've also added in there a couple of other sites. One of them is Hornsdale, for your information. That is the big Tesla battery system that was supplied to South Australia within 3 months. And they're expanding that. Initially, it was put in with grid following inverters, but they're now moving it into grid forming inverters. And the other battery system is down in Dalrymple on the end of a feeder, and that is grid forming. So when the feeder down there collapses out, the wind farm, the local load, and the battery keep the lights on. So South Australia is completely, all the planning studies are completely done in electromagnetic transients with no co-simulation with transient stability. And in fact, all of AMO, the operator down there, the 5 eastern states are all interconnected together, and it's all modeled in electromagnetic transients. And I should point out that this is the trend of the future. The China South Grid, which is a fairly large utility, everything there is, all their planning is done in electromagnetic transients. Much, much bigger than anything in Australia. So that's the way the future's heading because of the complexity of so many wind farms and solar farms, and just about every third house has got a solar panel. And that's a big challenge. And in fact, in South Australia, if all their thermal units were to go out of service, they have as much as, if everything was going with sunshine and the wind blowing, they've got about 200% of their load can be carried entirely by wind and solar and batteries. So anyway, let's carry on a bit more with this example. Wait a minute, wrong direction. What our task to do with Electronet, which is the utility there, was to confirm that this would be a better deal than using the state's gas plants. Now, this is an article out of a magazine from down there. We were able to confirm that South Australian Transmission found it cheaper to put in synchronous condensers, the 3 synchronous condensers we worked on, than providing strength from gas-fired generators. They will no longer be needed to switch on just to ensure the grid remains stable. And as I said before, South Australia has the highest penetration of wind compared with the size of its grid than anywhere else in the world. Now, unfortunately, I can't show you any results on this, but I do have a similar result that is available that I'm going to show you. And that is coming up here. The impact of synchronous condensers. This is a system with and without synchronous condensers, the results. So the top plots of power and RMS faults show a case where there's a fault near the wind plant where there was no synchronous condensers and the short circuit capacity was pretty low. And of course, the wind turbines tripped out on their low voltage ride through, and the RMS bus faults went crazy. But when you put a sync condenser in, as Nick showed, that helps things a lot better. And we noticed this small little oscillation that showed up, an electromechanical oscillation. But the voltage recovered, if we spread it out long enough, and the RMS volt stayed reasonably good. So that shows the impact of what we can do with synchronous condensers, properly placed, located, and designed, along with the renewable-based resources that will be around, like South Australia. It's all over the place. So that basically is my presentation. And so thank you very much. And
all right. Well, hang tight, Dennis. Here we had a couple questions coming. In fact, this is kind of maybe for Nick and Dennis because Nick alluded to it as well. And then I have one for Nick to loop back on. And it really boils down to the issue of the the control systems for the synchronous condenser. What opportunities are there to address instabilities that you might run across in a specific application? So
I'll start off and then Nick can.
Okay.
Based on the experience I've had with the synchronous condensers up here in Winnipeg, they're critical, but the only thing we have on that is just voltage control. And it's the voltage control, the biggest factor. Voltage control and short circuit capacity that we add. The inverters in here into Winnipeg would not work without that short circuit capacity that they had. And in terms of faults, like on the AC lines down to Minneapolis, I've never known them to go unstable yet, but they could.
Nick, anything to add?
Yeah, I think the only thing I would add is that figure that the manufacturers of the condensers get crazy when people say, just tell me the price per kVAR. And they have a bunch of knobs in the design so that they can emphasize short circuit strength, steady state VARs, transient VARs. They can give you more or less inertia. They can do a whole bunch of things that will aid the stability or aid the efficacy or the problem being solved. So, be really careful to avoid the kind of monolithic, will a condenser fix my problem? That is too narrow and economically suboptimal. Get the right condenser designed for the problem that you've got. And Dennis already emphasized you got to put it in the right place.
Yeah. Okay.
Yep.
one final one for Nick, quick one. Our friend Ryan Quint pointed this out, that in your presentation, Nick, you had mentioned grid forming inverters, but without a sort of clarification. And given our audience, maybe we just want to, provide a definition of what you mean by grid forming versus grid following.
Yes. Well, sadly, I am unable to give a really short, complete answer to that. Preternaturally incapable of giving short answers. It's one that will synthesize a internal voltage phaser and control it to some output. So that's the best shorthand I can give.
No PLL.
No, it's a PLL, but the PLL does something different.
Right. Okay. It doesn't use voltage to synchronize.
Yep.
Okay. All right. Well, we're going to hear more about applications as we move along. Obviously, South Australia is at the bleeding edge with regard to renewable integration, but our folks in neighboring country of Texas have been on that track for some time, and at previous ESIG meetings, they've always contributed to the thinking with the problems that they're currently experiencing, addressing, and the challenges that they see coming down the pike. So we have Fred Huang from ERCOT, who's been with them since, let me check my notes here, I think 2006, as a staff engineer in the organization, is going to tell us about their synchronous condenser experiences. Go ahead, Fred.
Hi, everyone. So I think first, thank you for having this opportunity. And I think the Nick and the Dennis presentation cover very well on the groundwork and a lot of very good discussion and experience. So kind of really good transition for me to share our experience on the synchronous condensers application, mainly for the purpose for the renewable integration with grid applications. So as always, I kind of try to start with some quick numbers, and before I kind of jump into the application in the synchronous condensers. So in ERCOT, I think many of you are very, very familiar with our system. If not, at least kind of give you a very high-level overview from the system load label and the renewable demonstration purpose. So our peak is close to 75 gigawatt. Just we set it up in last year, 2019. And we do have a lot of renewable generation, especially the wind generation in ERCOT. So the number-wide, the highest output from the wind generation breaker, we kind of exceeded 20 gigawatt. In terms of instantaneous penetration, we are very close to 58% already. So this this one drive the a lot of renewable integrations and the need of the system, including the synchronous condensers in ERCOT region. So another high-level background is the application we consider for synchronous condensers actually is in the area we call it Panhandle region in ERCOT. There's a unique characteristics of this region in West Texas of the ERCOT corner. High-level summarize the characteristic of the Panhandle. It is really a remote area. It's remote from the synchronous generators and the load centers in the ERCOT footprint. And in that area, as you can see on the bottom right, is really the historical renewable generation addition committed to connect to the Panhandle and the nearby Panhandle region. As of late last year, I believe as of now, the total capacity committed is expected to exceed 10 gigawatt. And as a factor right now, I think we already have close to 7 to 8 gigawatt they are in operation right now. So to look at that region, really everything is inverter based on the high renewable output scenario. Synchronous machine loader center, they are far away from this region. So obviously all the output will export out of this region. So it's really like a gigawatt level power export out of the Panhandle region On top of it, similar to kind of previous Nick's presentation, the power need to go through kind of transfer to a load center. In this case, it's 100 miles power transfer. So it's gigawatt power through 100-mile transfer from the inverter-based concentrated area to the load center in ERCOT. So obviously, no mention the kind of don't need to repeat, but really the two key challenges can affect the export capability out of the panhandle / nearby panhandle is really the concern of the weaker grid and obviously the voltage stability as well. So these two are really the drive point for us to start to consider what are the options in terms of upgrade or improvement to improve the system from the stability and the export capability perspective. So kind of similar to Dennis mentioned earlier, so when we try to identify the system upgrades to improve the area, both the typical dynamic stability such as PSSE or PSLF, positive sequence type analysis, and the EMTP, the PSK analysis were conducted for the panhandle and the nearby panhandle regions to ensure we properly capture all the inverters related with the grid issues, and we can identify as a result to determine the right technology. In this case, when we consider panhandle improvement with condensers, it was around 2014, 2015 time. So although we recognize the potential improvement of the controllers, but consider the commercial availability and the maturity at the time, really the technology was considered in that time frame. We focused mainly on the synchronous condensers, SVC, and the STATCOM to determine what is the right technology and where is the right location, and also what the spec of this device should be considered. So as a result, condensers kind of got selected out of these three, mainly for two kind of purposes: is to provide the system strength in terms of short circuit power. At the same time, they also provide a dynamic reactive support to improve the grid stability. That's really the two major driven points to determine the need of synchronous condensers in panhandle. So once we determine the condensers need, really in terms of implementation or the selection of the synchronous condensers, here just give a very high level overview to the group. There are many items not on the list when the condensers were selected or implemented. So obviously, as always, the first consideration is for the device, as the condensers here, what kind of system benefit they can provide to the system. In this case, they definitely improve our stability in the panhandle. As an obvious outcome is we are able to export more renewable power to the system at a lower cost. And as always, as a transmission upgrade options, the capital cost of the device must be considered. And when we were exploring the idea to have a need of condensers, a pretty interesting topic was among the time horizon is, do we want to go for the new one, or there were several available very older synchronous generators they may be able to retrofit to fit the need. So those were also considered during the selection process. And obviously, because the area is kind of in a remote area, so the availability, maintenance, operational expense, those are all need to be considered. So, and another kind of unique one is unstaffed and the remote control features were highlighted as one of the, I would say, first need, because given the remote area, so it is expected unstaffed and be able to have enough flexibility to remote control the condensers. So as a result, today we do have two condensers. They were implemented in 2018. These two are almost identical at the two locations inside the panhandle. So relatively the size is past around the 175 megawatt reactive support. In this case, we do specify and that have a desire, have a higher fault current can be provided by the condensers in panhandle to improve the strength and allow the inverters to operate under weak grid condition. So when we identify the condensers in the panhandle as a need, in the study horizon, we recognize a potential need. Otherwise, since we start having condensers in service and is in the process, consider maybe we may need to consider additional condensers for broader inverter-based concentrated area. Something we'd like to share with the group is, I would just say, it's not always, but I would say typically synchronous condensers, they do not have a PSS. And similarly, today, inverter-based, they also do not provide a PSS like, for example, the power oscillation damping functions in the inverter-based resources. Along the high penetration of inverters, the diminished online synchronous machines kind of also make the system with less and less damping support. So the simulation result shown on the slides, just as one example we observed in the stability analysis is the scenario. Look at the map on the bottom is we have a high penetration of inverters output focused on in West Texas. So in that whole region, we only have inverters and synchronous condensers too in Panhandle. Going through a high transfer to load centers where is in the east part of Texas. There's synchronous generators and the load centers. So really, during the disturbance under high long distance transfer, the oscillatory response start to kind of become more and more severe to a point really the stability related to the condensers can be of a concern to become a constraint in the near futures. So I just kind of want to share with this group kind of the way we are currently exploring the idea how to have options or mitigation to improve this one. So kind of key takeaway is that we do have condensers kind of to provide a system strength and improve the grid voltage stability, but they are synchronous machines, so they are susceptible to typical angular and inter-area oscillations as well. So especially under large power transfer over long distance, and this condition is commonly associated with renewables in many other regions, at least in ERCOT. So really, when in the future, I would say when we try to consider additional condensers application to improve the system stability over stress, I think a lot of synchronous machine stability related issues need to be really exempted, and also should consider to explore the idea how to have enough sufficient dampings if condensers try to be added into an area where only inverter-based or FEC device on the transmission side can provide a long-distance transfer. So that would be kind of my summary of this one. Thank you.
All right, Fred, thank you much. I'm going to resurrect a question that I botched a little bit before because I tried to paraphrase, and I think you queued up some more information for us to consider. And it really involves, with regard to a synchronous condenser, what opportunities we have for real-time control to potentially avoid, dampen inter-area oscillations, other instabilities that we anticipate encountering with their application. So I turn this back to you, Fred, but as well as Dennis and Nick, and for that matter, the other panelists as well, if they have some insight on that.
So I will try first, and definitely have other SMEs to help. So the condensers we have in Panhandle, we do not have PSS because at the time, I think based on our understanding and as I said at that time, it was really not very popular to have a PSS with quite a few reasons from the physical side due to the condensers without the shaft, and also how effective the PSS will be on the condenser side. So this is the one we are currently working on. But I think the way we are working on is, in general, we are thinking where we can get a damping if we still have this kind of damping needs in the system. So not only the condensers, we kind of explore the idea is like SVC STACON, they may have be capable to provide POD, and similarly the inverter base, because that's the biggest resource we have in this case as well in the region. So that's kind of my feedback.
Nice. Nick, any comments on that?
Yeah, just two real quick ones. As Fred said, the putting of PODs on SVCs and STATCOMs is, that's somewhat established art. It's not easy because the modal controllability is sometimes not great, but depending on the, in simple systems like my cartoon, that can really help. Then the other nickel I'll just toss out, because this could be news to a lot of people on the call. I'm always harping about inertia not being your friend, but there are times when inertia is your friend. And it is my understanding that at least two of those new condensers in South Australia have inertia, have flywheels or inertia enhanced condensers. So they have a H constant on the order of 8 instead of 1. Huge inertia. That's a two-edged sword, but in the case of South Australia, it's quite beneficial. So that's one of those trade-offs.
That's not controls, but it's actually a...
Yeah, it's actual design again.
Yeah.
And you got to design for that big inertia, but the inertia constant of H makes a big dent in their high rock-off problem. So people know about it.
Hi, this is Shruti. If I may add a quick point, at GE Energy Consulting Group, we have worked on a project where we have equipped a synchronous condenser with PSS to damp out some inter-area oscillations, and I have a slide on that in my talk.
Okay.
I'll go over some.
Well, you're coming up right now, Shruti, so that's actually a nice segue. Shruti is a senior engineer at GE Energy Consulting in Schenectady. She's involved in developing and improving GE PSLF, as well as conducting dynamic studies and other modeling activities. And she came to GE from Arizona State University, where she got her PhD. So I'll turn it over to you right now.
Thank you. I hope my audio is better now than it was earlier. So I'll be talking about some of the applications of synchronous condensers in these evolving power systems as we have more and more IBRs based on some of the work that has been done at GE Energy Consulting. And so historically, synchronous condensers have been used for providing variable steady state valves with the purpose of having voltage regulation as we've been shipping power over longer and longer distances. But as the grids are evolving and as we are having more and more inverter-based resources, some other inherent properties of synchronous condensers are proving to be helpful for the grid, which I'll be talking about. Some of these have already been discussed in great detail by Nick and Dennis and Fred. So I'll try to not repeat the points that have already been made. So the first helpful feature of synchronous condensers is short circuit contribution. Now, as we have more and more IBRs that are located far away connected by long transmission lines and that have very limited short circuit contributions, current contributions, the strength of the grid reduces. But a lot of these IBRs, which are current controlled grid following, do need the grid strength to be able to operate reliably because they rely on being able to latch on to the grid voltage angle so that the current can be injected at the proper phase. Additionally, you have these fast active and reactive current controllers, and which the current controls might become oscillatory, especially if your controls are faster than the system dynamics. Right, and there's an example down here where we had 3 wind plants connected near an SVC that was connected by a very long line, and when a fault was applied, it prevented recovery post-fault because we saw these very high frequency oscillations between the SVC and the wind. Now, this same setup was stable in a stronger grid condition, in a stronger operating condition. That is not to say that this is increasing the short circuit ratio is the only way to deal with these weak grid issues. Properly configured power electronics are very powerful and they can work in very demanding conditions, but they need extensive studies that can require a lot of time. Synchronous condensers, on the other hand, are very easy to apply and also very easy to model, right? Because the synchronous machine models, the generic models, have been around for several decades. They are fairly mature in contrast to the IBR models that we have, which as we speak are continuing to evolve. We are still developing them, testing them, so on and so forth. So synchronous machines is an easy solution that provides a good short circuit strength to the grid. And some transmission owners might be required by regulations to maintain a minimum short circuit level. Even under N-1 and -2 conditions, you might be required to maintain a minimum SCR level. And that's where synchronous condensers are found to be helpful. Now, this might be at either a new plant that is being connected. So you might want to increase the short circuit strength at the point of interconnection with the help of a synchronous condenser, or as you already have more and more IBRs at the transmission level, the short circuit strength is reduced. So you might also, the synchronous condenser might also be connected at the transmission level. That helps the improve the grid strength. And this grid strength helps not only in reliable operation of the IBRs, but it also helps in proper operation of your productive elements. It also helps arrest some of the transient overvoltages on fault clearing, on switching events, and transients, that is the transients, right? Okay. The next feature in which synchronous condensers can help, and again, this is also something that Nick has already touched on, is by providing an increased inertia. Now, by themselves, synchronous condensers do not have very high inertia constants. They're typically in the range of 1 to 2 seconds, but there have been projects where with the help of a properly designed flywheel, we've been able to improve the inertia constant or increase the inertia constant from 1.2 to as high as 8.7. And that is something that helps not only limit the rate of change of frequency, it also helps limit the rate of change of the voltage angles because your system is generally stiffer because of the increased inertia, increased short circuit strength, and that is helpful for the operation of IBRs. As we discussed earlier, they need to be able to latch on to the grid angle properly, to the voltage angle properly. So this is an example on the right here where we had a roughly 300 MVA synchronous condenser, which on its own had a inertia constant of roughly 1.5, a kinetic energy of 460 megawatt second. But enhanced with the flywheel, we were able to get a kinetic energy of 1750 megawatt seconds, which roughly translates to an inertia constant of about 6 for that machine. And that is very much comparable to a traditional power plant, like a coal-fired power plant, of 400 MVA gives roughly the same amount of kinetic energy, right? And the one thing to mention here, I think, would be that as opposed to synchronous generators, once the inertia response dies out and once you have the primary frequency response that kicks in that helps re-accelerate the machine back. But in the case of synchronous condensers, that after about you can allow it to decelerate for a few seconds, but at some point it has to re-accelerate back to synchronous speed, at which point it will draw some power from the grid, right? And the inertia, the flywheels are usually encased in their own vacuum casing, and that's primarily to prevent or reduce windage friction and heat losses and so on and so forth. Okay. The next aspect is dynamic voltage recovery. Now, after a fault is cleared, the transmission system needs a large amount of reactive power contribution to recover from the low voltage condition. Now, shunt caps and also SVCs, once they run into their limits, the reactive power output is directly proportional to the square of the voltage magnitude. So when you are in the low voltage conditions, it is even more, the reactive contribution of these devices is further reduced, which can be an issue and which makes it difficult for the voltage to recover, especially in weak grids where you may with higher percentage of motor loads that are prone to stalling. This becomes an even bigger issue. STATCOM has some overload capacity where it can provide an overload output for fractions of seconds to a couple of seconds. But even STATCOMs, if you have more severe faults or faults that are for extended durations, STATCOMs might also not give you as good a dynamic voltage recovery response as synchronous condensers. Synchronous condensers can take up to 1.5 to even 3 times the nameplate rating for fractions of seconds to a few seconds. And the higher overload capability is more with static excitation rather than brushless. And this is an example here where it's on a small system. There's roughly 200 megawatts of load, half of which is induction motors. And you can see that, of course, with no compensation, which is in blue, there is no voltage recovery. Now, the condenser and SVC give comparable response, but you will notice that the condenser has to be of a much smaller rating. It's a 40 MVAR condenser as opposed to a 72 MVAR SVC to give a comparable response. And even in that, you will see that in the initial portion where you are grappling with that low voltage issue, at that time, the condenser gives a faster response. The voltage recovers faster than it does with the higher rated SVC. And after that, that's because the SVC is grappling with the low voltage issues. And then after that, both of them are comparable. The SVC settles at a slightly, with the SVC support, voltage settles at a slightly higher value. Generally, this improved short circuit strength that comes from the synchronous condensers also is something that helps with the post-fault voltage recovery. And also, there are some systems that require your reactive support devices to be online through severe faults or extended faults, and that is something that synchronous condensers are capable of doing. Right. This slide is about damping, and that might be something that Fred might find interesting. So generally, even without PSS, because synchronous condensers are leading to a higher short circuit strength and a higher inertia, it causes your system to be stiffer, which generally can help reduce the oscillations between different power electronic equipment even without a PSS. And traditionally or typically, synchronous condensers are not equipped with PSS because they do not have a participation in the active power. The only active power interaction is primarily loss what they absorb for covering up for the losses. But we, at Energy Consulting Group, some of my colleagues have worked on a project where the synchronous condensers were equipped with a PSS to damp out the inter-area mode of oscillations, which the synchronous condensers does not necessarily participate in, with the two sets of machines interacting with each other. So that involves designing the PSS and tuning the PSS involves a lot of small signal stability studies where you have to look at the gain margin, phase margin, and root locus. So without going into too much detail, this is a quick example where I hope the numbers are visible on the screen, but you can see that in the base case, there's a set of roots 1 through 8, and these poles of 1 through 8 are with increasing gains of the PSS that was equipped on the synchronous condenser. So you can see that in the base case, without any PSS, that is with a gain of 0, that's point number 1, there's this set of poles which is very, very close to the right half plane. So that's a very poorly or almost undamped oscillations without PSS. But in the n-1 condition, which is the root locus on the top, you can see clearly that the point 1 is on the right half plane, which means you're going to have negatively damped oscillations for that mode. But for about the same frequency, as you increase the PSS gain, you can see point 2, which is the gain of 2, has moved slightly into the left half plane. So that's reasonably damped, and then 3 and 4 is further damped. And as you increase the gain beyond that, as you increase the gain beyond 10, that causes the mode to swing back and go to further to a poorly damped. And you can see that the gain of 6, 7, 8, that's gains of 20, 40, and 60 are clearly unstable. They are negatively damped. So for this particular project, with the objective of getting sufficient damping for this inter-area mode and also maintaining sufficient gain margin, we went with a gain of 5. And you can see the results on the right where there was a fault and then one of the lines was cleared. Without the PSS, that's in orange, you see these negatively damped oscillations. With a properly tuned PSS, that's in blue, the oscillations are very well damped. And the damping gets even better if, so there were multiple synchronous condensers here, and the damping was better if both were equipped with PSS as opposed to only one. So that's an example of a thread where we were able to equip the synchronous condenser with PSS and effectively damp out an inter-area mode of oscillation. Finally, this is something that Nick did mention when he was answering one of the questions. When we talk about synchronous condenser, just because you need a higher short circuit contribution or you need improved dynamic voltage recovery does not mean that you need to increase the nameplate rating of your condenser. That's because the short circuit contribution of the condenser is primarily going to be the internal voltage magnitude divided by your net subtransient reactance, which includes your condenser and your transformer reactance. So the point is that you could have a smaller rated machine with a smaller reactance, smaller subtransient reactance, give equivalent or sometimes even better short circuit contribution as a larger nameplate machine, but a larger reactance, right? And also likewise, if you want to improve the dynamic voltage recovery, you could try try designing your condenser appropriately with smaller reactances, perhaps smaller time constants, or more aggressive excitation systems, increased field forcing limits, or using static excitation systems, so on and so forth. So you don't always need a larger machine. You can get away using a smaller machine if you're focused on the short circuit requirement, and you don't need that higher output sustained for a longer term, because over a longer term, you can't exceed the nameplate rating. For a shorter term, you don't need that large nameplate rating. So it means you can have lower cost and lower losses. That said, sometimes by the time it is realized in a project that a synchronous condenser is required, there may not be sufficient time to optimize the design of the condensers, and you may have to go with something off the shelf. So just to quickly summarize, we are very familiar with the use of synchronous condensers for variable steady-state VARs for voltage regulation, but these boxes in 4 are some features that are found to be more helpful with more and more IBRs. And by no means do I mean to say that these are the only solution, that synchronous condensers are the only solutions to a weak grid or lower inertia or whatnot, but they can be a viable solution. They can be an easy to study and easy to apply solution, right? The short circuit contribution helps proper operation of IBR, proper operation of your protective elements, and reduces the transient magnitudes. So because synchronous condensers can give increased output for the short circuit and short time after the fault is cleared, it helps with the dynamic voltage recovery. Especially, they can provide a better response even under depressed voltage conditions, which is helpful. And that performance is usually better than SVC or STATCOM of the same nameplate rating. They help increase the inertia, especially if they're equipped with a flywheel. They can help increase inertia, which helps frequency stability and also helps make the grid stiffer, which is helpful for IBR operations. And lastly, damping, where the generally stiffer system itself leads to reduced oscillations between power electronics, but on top of that, we can equip these synchronous condensers with PSS to damp out some inter-area modes of oscillation. So that's a very brief summary of the talk. That's it from my end.
Okay, thank you, Shruti. We're just a little bit tight for the schedule time, so I'm going to move on. But let everyone know that all the questions submitted will be answered and sent back out, and then we'll see when we're done here what opportunity we have to pick a few more up. Our final panelist is Vahan Gevorgian from NREL. He's a chief engineer with them since 1994. He served as principal investigator on multiple research projects, a lot of them dealing with renewables integration, including wind, solar, energy storage, hydropower, and grid modernization. So I will turn it over to Vahan to bring us home.
Thank you, Bob. And thank you, Charlie, Bob, and everyone for inviting me to be part of this panel. And also thank you for being so flexible and moving ESIG into virtual domain. Nothing like in-person meeting, but broadcasting to 160 people from the comfort of my basement is kind of cool here. So let's see if I have a control here. Oh, still cannot move the slides. Did you guys give me a control?
Yes, it's over on the left.
Okay.
There you go.
Okay, it works now. So, great discussions from previous speakers about the role of synchronous condensers, grid forming, overall stability, and so forth. This issue of the role of synchronous condensers in a grid, I think it's part of a bigger picture, and all these new technologies that we're trying to evaluate and understand their role in our, existing and the future grid is part of a larger set of questions. And here I have a long list of those, and it's very likely not exhaustive, of course, but the point I'm trying to make, you can't study one technology in isolation from another, one service in isolation from another. It's kind of an overarching issue. So here I highlighted in red the questions that are more relevant, I think, to the main theme of this session. But role of synchronous condensers in particular, I think, depends on where we are in time on our way to 100%. Characteristics of particular systems, and even when we get to 100%, how we operate the system, And this all runs probably in a more fundamental question is like role of frequency in a future system, low inertia, zero inertia grids. Is it still an issue, or we operate everything as a fixed frequency? So I think all that will impact significantly choice of technologies we use to keep a system going for both reliability and stability services. So moving on, the NRL actually developed a very unique, one-of-a-kind, validation and demonstration platform at NRL's Flatiron's campus. This is a kind of a high-level diagram of that, where we are trying to address all these issues by conducting testing, validation, and demonstration of different types of technologies at the scale. So we're currently pushing the system up to 27 megawatt level, which is very large for a demonstration system of this type. We're in the process of adding a 2 megawatt synchronous generator to a system, which one of the use cases for that, of course, will be operating it as a synchronous condenser. So we're using this setup to do characterization of individual technologies. This is one example of active and reactive power of a battery in both grid following and grid forming modes, and we use this type of test results to validate our models for both dynamic and transient studies. So one example of how it's done, this is a simplified model of a grid forming battery model that we're using for large-scale integration studies. The advantage of a grid forming, of course, is the grid forming is absolutely necessary when we're talking about the high penetration grids, because someone needs to set voltage and frequency. In particular, the grid forming operation by inverter coupled resources, in a way it's simpler because there is no things like PLL. They have autonomous load tracking ability. One thing is, of course, is the no ability to do a current control. This is especially true when you go through a voltage fault event. So in order to limit the current, you have to switch to a current limiting mode, and in that case, you are no more a grid forming source anyways. So we have used this model and models of our renewable resources developed and validated at our facility to do a number of studies. This is an example or one snapshot of one study we did for a PREPA in Puerto Rico. This is the DOE-sponsored study looking at the very high-level penetration of bisolar. This is one IRP scenario for PREPA, and you can see that levels of variable renewable generation in the form of solar and battery storage is extremely high. 3.4 gigawatts of PV and over 2 gigawatts of storage on a system that is forecasted to have 2.2 gigawatts peak load. So there is only very few remaining synchronous resources left, a couple of combined cycle units, and also the picker units. As part of the study, we also looked at the what role the synchronous condensers can play in this system in order to invest stability. So we looked up to 300 megawatts of synchronous condensers in this system. So in this particular case, we converted the PSSE model into PSCAD, so all simulations were done in PSCAD. We're not using a PWM model for these units because of a large size of the system, but the plan to do so when we switch into parallel computing, as Dennis mentioned. All grid forming, all battery systems in this case are grid forming, and they're operating in a frequency powered loop. And they're also connected to AGC in the island. And in this particular dispatch case, the PV is almost at its peak, so the battery is essentially acting as a load and it's charging. And also we consider a case when some PV plants are curtailed a little bit by 5% or so to help grid forming storage to provide enhanced services to the grid. For the synchronous condenser modeling, we started looking at different options, and also in looking into a hybrid type of architectures for synchronous condensers when you operate it in parallel with other technologies, such as STATCOMs, small or big storage. The advantage of hybridization is that you can get the best use from more than one technology. So I think hybrid with BSS, with battery energy storage, converts the STATCOM into more superior technology, because having the ability to control both active and reactive power and have very large overcurrent capability, I think it is a winner. Of course, this comes at a cost. So we look at this option in this Puerto Rico case, and for some large battery plants, we enhance them with the synchronous condensers, for that matter, and we call it so-called superfacts type of technology. Here is how we developed the model. This was actually again done in a PSCAT. This is a simplified diagram. So it's a modular approach. We have number of 50 MVAR synchronous condensers equipped with high inertia flywheels, and they can be combined in a modular plant of any size, where you can actually set both inertia level, desired SCR levels at the point of interconnection, and also tune up your AVRs for desired voltage stability considerations. This is pretty much the approach adopted by ABB in their commercial systems, and the system. One example of that system of high inertia synchronous condenser is shown on a photo. So we did a number of simulations. Here is one use case where everything on the island is essentially PV and grid-forming storage. There is only one remaining combined cycle unit operating, and at that moment, we lose about 250 megawatts of PV, several very large PV plants in one part of the island. And this is two cases where the 300 megawatt MVA synchronous condensers were distributed along the island and no condensers. So you can see that the system recovers okay at this very high penetration case. This is because of the grid-forming battery systems. As far as the frequency response itself, there is very little gain in terms of nadir and the Rokov. This is mainly because of the inertia of the synchronous condensers, but it's not very critical. We looked at the next case where we essentially actually dropping that last remaining piece of inertia in a system, and everything in that is essentially 100% inverter-based. And again, this was done with and without synchronous condensers, and you can see the system response. And again, the gain from synchronous condensers in terms of frequency response itself is not very significant, because I mean, it could have been significant if you put more and more synchronous condensers and adding inertia, but again, it all comes at the cost. And one interesting case is this one, when again we drop the last remaining combined cycle unit, and that PV plants that happen to have 5% headroom provide both inertia and droop control. And now you can see that all of a sudden the frequency response is significantly better than in previous two cases. Frequency nadir is low, recovery is okay, but you probably can see these oscillations in a case of the synchronous condenser case, and that's kind of echoing with things that other presenters, were talking about, that there may be some control interactions between condensers and grid forming and other inverter-based resources. In this case, it's damped and system recovers, but there might be situations that we didn't model, then this can become a stability issue. So all these use cases essentially are combined in this particular graph. So basically you can see that in terms of frequency response in this system that is basically 100% inverter-based grid, the synchronous condensers don't provide much benefit, right? So this grid-forming battery system is capable of riding through this and providing fast recovery. And on the lower graph, you basically see the response of aggregated response of all battery systems on the island for all these use cases. So it appears that in this very high, almost zero inertia grids, the value of condensers will be more in the area of short circuit current contribution, short circuit ratio boosting, and voltage stability. And indeed, we run a number of cases for that too. So this is output of one plant that was exposed to a fault that happened somewhere on their 230 kilovolt line, with and without synchronous condensers. So you can see that short circuit current level in the case with synchronous condensers is much bigger, which is good for protection. And system rides through it okay. But another drawback here is that In case of synchronous condensers, there is a much higher transient in voltages during recovery, and that makes it complicated for these grid-forming battery inverters to come back to their pre-fault power level. This is why you can see on a lower graph on the right, actually, it takes longer time, a couple of hundred, maybe 300 milliseconds or so for the grid-forming battery source to come back online. So again, this is you need to look at this problem from both sides. You provide short-circuit current, but in the same time, your synchronization back to the grid might be delayed because of the high level of transients. So in terms of short-circuit ratio boosting, we didn't do that particular study for Puerto Rico, but this is an example of a study we participated with the DTU in Denmark on a role of synchronous condensers and their optimal locations in a Western Denmark power system grid. This is a model of their 400 kilovolt transmission system in a Western Denmark, which is also going through rapid transition, a lot of HVDC lines coming in, existing and coming in. Generators will be retired, a lot of wind coming up, so the short-circuit ratio is degrading. So we conducted analysis on what is the best way to maintain the voltage stability and the system strength for this particular system, which eventually ran into a simple optimization problem. So to find the lowest cost solution to ensure that the short-circuit ratio criteria on each bus is met, which was short-circuit ratio above 3. So number of scenarios in this table you can see, and the associated cost and MVAR ratings for synchronous condensers. To make it short, the black line on the bottom on this graph essentially the base case, and you can see that there are two systems that are two buses in a system that are very weak. But when we run through this deployment plans, you can see that, of course, a different cost, but it's possible to keep every single bus to meet that short-circuit ratio criteria. In addition, the transient performance of a system improves too. There are a couple of sample buses here, and the black one is a system response with synchronous condensers, so you can see it's less voltage drop and also better recovery process. So in order to address this type of issue and many other issues that we talked about, going back to NRO capabilities, this is more detailed view of this validation platform we developed that consists of grid simulators and also the real multi-megawatt scale, multi-megawatt utility scale renewable generation and existing energy storage. And as I said, we're adding a 2-megawatt generator to one of our dynamometers to make it to operate as a synchronous condenser as well. So I think this is a platform where many answers in terms of the controls testing, controls validation, and model validation can be done at the scale. In addition to that, things like black start strategies, other resiliency controls, and so forth can be done as well because number of these units here is grid forming. And in addition, we're doing work with the GE right now to develop a grid forming controls for one of their wind turbines at the site and actually also demonstrate it at the scale. So speaking of wind, there are a number of wind turbine topologies out there, most common, of course, Type 3 and Type 4 nowadays. And many vendors are now doing work and research on a grid forming aspect. So these demonstrations be done in Europe. As I said, we work with GE. But one point I wanted to bring up here is essentially one possible solution that is coming away from a past, also worth looking at, the so-called Type 5 wind turbine, which is a turbine with no power converter but synchronous generator. So this might be a useful topology if it's available to system planners and project developers to a certain levels of at certain levels of penetration on our way to 100%. This technology has been demonstrated in the past. In fact, NRO tested one of the first 2-megawatt units at our site. Basically, that was a drivetrain from a D-Wind. But that's basically a synchronous generator-based wind turbine with a hydraulic torque converter. So it operates basically as any conventional plant. It can also provide synchronous condenser-like services at the times then there is no wind. So I'm not saying this is a solution, but this is something maybe worth considering. And essentially going back in time and see if this now old technology makes sense. In fact, few of these turbines have been deployed also in the Sweetwater in Texas. The company, the wind doesn't exist no more. It's been acquired by Koreans and then so forth, but the idea is still there. So something to think about. And going back to my last slide, which is the summary, as conclusion, pretty much everything what I just said. So grid forming capability by inverter resources is very important it's absolute must, I would say, for system stability with no inertia grids. Determining the optimal ratio between grid following and grid forming is still a pending question and is probably, again, very system specific. Research is needed to quantify benefits of this hybridization idea in asynchronous condensers and their controls for system stability. And then what is the value of synchronous condensers in extremely low and zero inertia? You saw in the case of Puerto Rico, at least from a frequency response perspective, the value is not that large. And also testing and demonstration at the scale is very important, and that's where the NRL and other national labs come into play. I think this is all I have. Sorry if I went over time, and thank you.
I think we're fine. So, Vahan, you don't know if we're going forward or backward, huh?
Sometimes it makes sense to go back.
Yeah, okay. So, thanks for that. We're over time, but we probably have maybe 5 to 10 minutes for questions, and I'll kind of keep track of how many folks are hanging in there to gauge when we wrap it up. Picking up a question that was left, and I'll just read it verbatim rather than paraphrasing, and this would be directed to all the panelists. It seems that a large number of smaller synchronous condensers on the distribution system, e.g. one at every substation, would offer stability and control advantages over several very large synchronous condensers on the bulk system. Your thoughts? Do we have panelists left?
Well, this is Ani again, if nobody else is answering. I think, the distributed resources, they require distributed support, so I think it's a really good idea. The use cases I presented was more like a large transmission scale, but I believe for largely distributed resources, having synchronous condensers is very important for both voltage stability, but also for a short circuit current contribution as well, because it's an essential part of the reliable protection operation. And the trade-off there is you either put synchronous condensers to provide short circuit current and operate protection in an old way, or then you have to upgrade your whole protection and go into more advanced ways, communication-based or whatsoever. So I believe it's a good idea for distributed generation.
Okay.
I just make a quick comment. I think, I'm wary of decisions to maintain or have high maintain short circuit level to keep old protection paradigms in place for another generation. But other dynamic aspects, particularly things related to, FIDVAR, for example, having the control, having the support be closer to the loads should give you a rating advantage. Of course, it's got to be balanced against the intrinsic cost, that loss of scale. So it's a good question. I'm not sure that it's obvious which answer is best, but we should be asking the question.
Here's one that's a little off the topic of synchronous condensers, but I think it's relevant to the larger picture, and I'll read it. I believe STATCOM was originally designed as a grid-forming voltage source described by Hingorani's book, Understanding Facts. Why did manufacturers design them as grid-following inverters? If we go back to 20 plus years ago when we started to plant wind in the ground. Any thoughts?
Yes, this is Dennis. Okay.
You've been hearing me say for years, grid following inverters make very good use of the rating of the converters, and they play nice together.
Okay.
So that's two of the reasons for that.
Okay. Dennis?
Yes, I was going to suggest that the StatComs, if you really want to make them work as grid forming, you need a bit of energy in the DC side, which could be a small battery or a super capacitor.
Yeah. Okay. All right. Let's see. Let's find another one here. This was directed to Nick and Dennis. Can one of you comment on to what extent inverter saturation, parentheses, control minus duty minus saturation, not quite sure, affects performance of IBR-dominated grids, and how much detail required for the inverter model to accurately predict these effects?
Well, this is Dennis here, and we always, in our big studies, always get the manufacturer's exact models of their turbines or solar panels or batteries or whatever. And if we find, as we often do, that their system doesn't work, we go back to them and have them fix it until it does. And it might take 3 or 4 or 5 or 6 turnarounds with the manufacturer before we can get a system working. And I would expect the same thing would happen as we go into this kind of situation. There should be a solution. And I don't know what it is right now.
All right.
I have a comment, I guess, maybe it's a different face, the same thing that Dennis just said, and that is, there's a lot of discussion in the industry about what the current rating of the grid forming inverters should be. And it seems clear to some, myself included, that just throwing money at the current rating of the converters so that they can deliver, for example, as much short circuit current as a synchronous machine is uneconomic. So we need, as an industry, to have a good handle on the behavior of, and I think that was in the question, the saturation. When these inverters hit limits, and they hit current limits and they hit power limits, is the behavior beneficial? Is the system, or are there pathologies that go with going into limits, and are there other pathologies about coming out of limits that we haven't figured out yet? I feel like we got more homework to do.
Okay. All right. This one would be directed at least towards Fred, and it's what is the impact of the 1.8 hertz oscillations in the ERCOT system? Are they caused by IBRs or the power system stabilizers installed in synchronous generators in the network?
This right here. So that particular case was one of the outcome in the stability study we conducted for the Panhandle region, and we did some kind of check and test. And already the participation in this case is 2 synchronous condensers kind of against the rest of the ERCOT remained synchronous machines in the study case. And because the 2 synchronous condensers, they kind of embedded in more than 10 gigawatt inverters, so obviously the rest of the wind output also got affected associated with that 1.8 hertz. But already in terms of the participation, in that case particularly is synchronous condensers, in this case, which we do not have a PSS, against the rest of the ERCOT synchronous machine.
Okay. All right. Thank you for that. Let's see. I'm going to do one more question, and this would be to everybody. I know what Dennis's answer is already, but I'd be interested in hearing that again, as well as other folks. Do you see the industry moving towards co-simulation, that is phasor plus EMT, or eventually will we do just full EMTP simulations? And I'll add to that, what do you see as a transition time for this, given the sort of inertia, if you will, that we have in our present models, study tools, and whatnot.
This is Dennis here. I think it's a temporary process only. I think eventually we will have to all go electromagnetic transients, high-speed electromagnetic transients, in another 10 years.
Okay. Anybody else?
This, Fred, I can share a little bit. This is something we are going through right now. So in a region like Panhandle, at this moment, we start to conduct the stability, always include the PSC and the PSK together. If nothing else, just make sure the typical positive sequence model and the tool, they are still aligned well with more detailed EMTP. But with the system got bigger and bigger in terms of inverters, we do start to have a concern in terms of a computation burden and also the capability to scale up that studies in a timely fashion, managing the potential need is going to the real time. So obviously, anything can be improved in terms of better model representation in a typical positive sequence or more efficient computation in the EMTP or something new. That's something we are experiencing right now. Thank you.
All right. Thank you, Fred. Well, I think it's about time to wrap up. I'll want to reiterate that we will address all the questions that were submitted, pass them around to the panelists, and get you responses that hopefully are on point and satisfactory. I want to thank all the panelists for their presentations today, and then all you folks on the phone for your participation. I would like to remind you that the next portion of the Tucson program, which is Session 3, Current Challenges with Transmission Planning, Where Are We?, will be held next Thursday, April 2nd at 2 p.m. Eastern. And as Charlie mentioned, you can find the full schedule of upcoming sessions on the ESIG website, esig.energy. Again, thanks. Stay safe, stay healthy. Let's get through this, and maybe Charlie can work up another good venue for us in the fall. Thanks again, folks.